In this section I will show you how to prepare production deployments. In the first video of the section I'm going to do a quick review of the main Kubernetes objects, such as pods, replica sets, deployments and services. Our application will have to be deployed to production eventually. In today's rapidly changing world, this has to happen rather sooner than later. Contrary to what is possible directly on a Docker host, you cannot run containers directly in a Kubernetes cluster. In a Kubernetes cluster, you can only run pods. Pods are the atomic unit of deployment in Kubernetes. A pod is an abstraction of one or many co-located containers that share the same kernel namespace, such as the network namespace. Co-locating containers can make a lot of sense when the containers are tightly coupled to each other and very chatty. Typical examples could be an application service in one container and then a so-called sidecar, a proxy service or logging service co-hosted in the same pod. Here I have an example specification of such a pod. This pod is called web pod and contains a single container. The container uses the image Nginx Alpine, Nginx being a very popular web server, and it listens on the container port 80. Let me run this pod using the kubectl tool. And that seems to be happened successfully. I can confirm it by using the kubectl get pods, and indeed I have this one pod running. I can now try to exec into the container and run, for example, a shell inside it. Let me do that. I need to use the name of the pod. I want to do it in interactive mode with an attached terminal, and I want to run the shell inside the pod. And indeed, I am inside the container now, and I can see the file system of this container. To exit the container, I can simply press Ctrl D, and I'm back on my host. I can also use kubectl to describe the pod to get more information about it. And I can shorten, instead of writing pods, I can just write PO, that's a shortcut. And here I'm getting a somewhat lengthy description of the pod with much information about its name, namespaces, and so on and so forth. Interesting is the events list at the end of this description, where I can see what happened with the container. Before we proceed, let me delete the pod, also using kubectl. So far so good. Let me clean the terminal. Now to the replica set. A single pod in an environment with high availability requirements is insufficient. What if the pod crashes? What if we need to update the application running inside the pod, but cannot afford any service interruption? These questions and more can only indicate that pods alone are not enough, and that we need a higher level concept that can manage multiple instances of the same pod. In Kubernetes, the replica set is used to define and manage such collection of identical pods that are running on different cluster nodes. Among other things, a replica set defines which container images are used by the containers running inside the pod and how many instances of the pod will run in the cluster. These properties and many others are called the desired state. Here on screen you see a simple application for a Kubernetes replica set. You see the kind of the resource is a replica set. Its name is RS Web, like ReplicaSet Web. This in general looks an awful lot like the pod specification we introduced earlier. But let's concentrate on the differences then. First, on line 2, we have the kind of which was pod and is now replica set. Then on lines 6 through 8, we have a selector that determines the pods that will be part of the replica set. In this case, it is all pods that have a label app with the value web. Then, on line 9, we define how many replicas of the pod we want to run. 3 in this case. Finally, we have the template section here, which first defines the metadata and then the spec, which defines the containers that run inside the pod. In our case, we have a single container using the Nginx Alpine image and listening on port 80. We can now run this ReplicaSet using kubectl. And it has been created successfully. Let me see what happened. Again, by using kubectl and the command get all. As expected, we have the ReplicaSet and 3 containers running. I can now forcefully try to disrupt the ReplicaSet by deleting one of the pods and then see what's happening. Let's do that for the first one in the list. I'm copying its name and do a kubectl delete of this object. If we do a get all again, we can see I have a new pod now. Here, this one, if you compare the first list above, here, this one, with the one below, this one is the new pod, which has replaced the one I deleted before. So the record set has automatically re-established the desired state. Before I proceed, I want to delete the ReplicaSet again. Okay, that has been done successfully. Let me clean my terminal. Okay, on to the deployment. Kubernetes takes the single responsibility principle very seriously. All Kubernetes objects are designed to do one thing and one thing only, and they are designed to do this one thing very well. In this regard, we have to understand Kubernetes ReplicaSet and deployments. The ReplicaSet, as we have learned, is responsible for achieving and reconciling the desired state of an application service. This means that the ReplicaSet manages a set of pods. The deployment augments the ReplicaSet by providing rolling updates and rollback functionality on top of it. Here on screen I have a sample specification for a deployment using the Nginx container image. It looks very similar to the specification of a ReplicaSet. But please note the strategy section on line 7 and below, where I have defined how updates should happen. In this case, it's a rolling update. Remember, we have used this technique in the last video about how to prepare your services for zero downtime updates. You might want to refer to that video to see a rolling update in action. We can create this deployment using kubectl, and we can try to see what happened by using the getAll command. As expected, we have a deployment and a ReplicaSet and the 3 pods running. Let's leave this deployment alone for the moment and move on to the Kubernetes service. In this diagram, the moment we start to work with application consisting of more than one application service, we have a need for service discovery. In this diagram, we have a web API service that needs access to 3 other services: payments, shipping, and ordering. The web API should at no time have to care about how and where to find those 3 services. In the API code, we just want to use the name of the service we want to reach and its port number. A sample would be the URL http://payments:3000 that is used to access an instance of the payment service. In Kubernetes, the payments application service is represented by a ReplicaSet of pods. Due to the nature of highly distributed systems, we cannot assume that pods have stable endpoints. A pod can come and go in a blink of an eye. But that's a problem. If we need to access the corresponding application service from an internal or external client, if we cannot rely on pod endpoints being stable, what else can we do? This is where Kubernetes services come into play. They are meant to provide stable endpoints to ReplicaSet or deployments, as shown here on the slide. In the diagram in the center we see such a Kubernetes service. It provides a reliable cluster-wide IP address, also called a virtual IP or VIP, as well as a reliable port that's unique in the whole cluster. The pods that the Kubernetes service is proxying are determined by the selector defined in the service specification. Selectors are always based on labels. Every Kubernetes object can have 0 to many labels assigned. In our case, the selector is up equals web. That is, all pods that have a label called up with a value of web are proxied. Here I have a specification for a Kubernetes service. We can create this service using the kubectl, and we can try to list everything. And here I see a line for the service that I have just created. It's a node port type of service, and it exposes the port 80 of the container to the host port 30,224. I can now try to access the service, and through it the Nginx server with, for example, the curl tool. And here you see I got the welcome page of Nginx. As a conclusion, this was a very quick overview over the most important objects that Kubernetes offers us to define and manage our distributed applications. These are the pod, the replica set, the deployment, and the service.